Okay. Okay. So it's already 1 o'clock, so let's get started. Yeah. Today is probably the only occasion that we are going to teach the class online. Okay. The reason is because like the school require like I mean, when we come back from foreign country, like we need to go through like a 3+4 quarantine, right? So normally, like after 3 days quarantine, I mean, we are supposed to be able to teach like the class in person, but the school recently tightened the regulations, saying like for the whole 3+4 period, okay, we are not able to, we shouldn't come to school, okay. And yeah, it happens that I caught a cold in Vienna, okay. So so you will hear that I cough like a lot, like I mean in today's lecture, but don't worry, because I'm pretty sure it's not COVID, okay, because I had like 2 rapid tests, like and both results turned out to be negative, okay. So yeah, it's I'm pretty sure like next week, okay, we will resume like um the regular teaching in the classroom, okay. So just so this week, okay, this online teaching will be only like just one-time thing, okay. So sorry about that, okay. so last time, okay, we talked about perceptron, and we also talked about the multi-layer perceptron, okay. But the issue about the multi-layer perceptron, okay, the idea of multi-layer perceptron was actually proposed like at the end of the first AI wave, okay. But at that time, people do not know how to train the MLP, okay. So it wasn't until like 1986, okay, uh, the second wave of the AI, okay, that like researchers found out like there's a researcher called, like, his name is D.E. Lumerhardt, okay. He has a groundbreaking paper published in 1986, okay. He proposed the idea of the backpropagation, okay. So this backpropagation training, okay, allows us to train the MLP, okay. And in the backpropagation training process, okay, the idea of the gradient descent was firstly used to train the model, okay, with what is called reverse mode autodiff, okay. You may not know what reverse mode autodiff is, okay. I will talk about that, okay, later, okay. That's one technique, okay, to to compute the differentiation, because obviously like during training you need to, when you use gradient descent, I mean, by now you should have like a little bit of idea what the gradient descent is, right? So during every iteration you need to identify the gradient, right? You need to compute the gradient. So the ability to compute the gradient efficiently, okay, is very important, during the training process. Okay, but I will get to that point later. Okay, so basically, what is this backpropagation? Okay, so the backpropagation process is done like this. Okay, so for each training instance, okay, the algorithm will feed the instance to the network and computes the output of every neuron in each consecutive layer. Okay, so basically, this process is just like, you know, doing the inference. Okay, but it's just like you need to recall like a state of every neurons pretty much. Okay, and that's the first step. Okay, and obviously, because as I said, this is the inference, right? So you will have the output, right? So in the second step, okay, we are going to measure. Okay, remember we are doing this, but I mean in a supervised learning process. Okay, what we call supervised learning is basically like we for especially for the training instances, we already know the real answer. Okay, so once you use like this network to do the inference, okay, the output you obtained, okay, will be able to be compared with the correct answer. Okay, so you will be able to estimate like how much error, okay, is contributed from each neuron in the in the output layer, in the previous hidden layers, pretty much like you can backtrack the error that is contributed by each neuron in the network. Okay, and this process, okay, is where the back propagation gets its name, because from the output, obviously you can measure like the distance between the output and the real answer and the correct answer, right? But you will have to propagate those error, okay, back to every neuron, in each layer, like in a backward fashion. Okay, so that's why it's called back propagation. Okay, so once you obtain like how much each neuron contribute to this error, okay, in the second step. In the third step is that you are going to, it's a basically gradient descent. Okay, you use that to decide like how you tweak the weight for each neuron, okay, to reduce the error, okay, to reduce the error for the inference. Okay, so to summarize, okay, if we want to use like short phrases to capture the idea of these three steps, okay, the first one is going to be forward pass. Okay, it's just like an inference, right? You have some instances and you know the answer of those instances. Okay, so you use the forward pass, okay, to obtain like the state of every neuron as well as the output. And the second step is called reverse pass. Okay, basically you measure the error, the distance. Okay, each neuron contribute to the error. Okay, so as I said, this is actually where backpropagation happens. Okay, and the third step is the gradient descent. Okay, you tweak the network accordingly. Okay, so that you reduce the error. Okay, so and keep in mind, like because it's a gradient descent, so this is it's going to be a loop. Okay, just like the gradient descent that we discussed like earlier. Okay, we actually have to run it like repeatedly. Okay, until the error is reduced to a acceptable range. Okay, so at that time, okay, we are we believe the network is able to help us to deal with the task that we wanted to do. Okay, so this is like you know, how the MLP is trained. Okay, so before training, okay, when you have a network, you want to train the network. Okay, remember, I mean, there are so many parameters, okay, for a network. Okay, the well, basically, what I'm talking about are the weights. Okay, um, that includes like the weights for every connection, as well as the weights for the bias. Okay, so all these weights, okay, it is very important. Okay, before training, we initialize all these connection weights in the hidden layers randomly. Okay. Remember, like in the gradient descent, we have like a random initialization. Okay, this is exactly just like that, just like that. But you know, in the random initialization that we talked about in the gradient descent, okay, you may feel like, well, if we start from like the case where all the weights are 0, it looks to us that it is still okay, right? But in MLP, if you assign all these weights to be 0, okay, we have some problem. Okay, why? Because all the neurons in a given layer will be pretty much identical, right? Because they have the same weights, okay? And the backpropagation will affect them, okay, exactly the same manner, okay? So this, you know, in some sense, okay, I mean, because backpropagation, I mean, affect each layer the same way. So they will basically, I mean, remain to be the same. So the whole network, okay, is reduced to, you know, to a much simple architecture. Okay, the whole layer, you know, will be reduced just like a one neuron. Okay, you lost like the diversity of your network. Okay, so this is something you want to avoid. Okay, you want to break that symmetry. Okay, so that's the reason. Okay, we want those connection weights to be initialized randomly. Okay, but okay, even when I say we want them to initialize randomly, there are some consideration for this randomization, for this randomness. Okay, so there are actually different random initialization schemes for this connection weights. Okay, I will get to that point. Okay, in the next chapter. Okay, in the next chapter. Remember, I mentioned about like the third wave of AI. Okay, you know, they are you know, some researchers, okay, propose some small tricks that allow the training of the neural network to be much more effectively. Okay, you know, some of those random initialization schemes, okay, are no what I mean part of these small tricks, okay, that actually help you to train the model much easier. Okay, but we'll talk about that, I mean, in the next chapter. Okay, so another important change, okay, they found out, okay, when they proposed this backpropagation, is that, okay, remember the previously when the MLP, the multi-layer perceptron was proposed, okay, it is based on the idea of perceptron, right? And the perceptron, remember the activation function is step function, right? So the step function, I mean, well, it works well for the perceptron, but for the multi-layer perceptron, especially when you use the backpropagation to train the model, okay, using the step function has some issue. Why? Okay, think about that. Okay, let's go back. Okay, to look at this backpropagation training process again. Okay, the third step of this backpropagation loop is gradient descent, right? So it is very important that you have some gradient. You have some gradient. I mean, or let me put it in another way, like a slope, right? I mean, if you forget most of your you know college calculus, at least you remember slope from your high school math, right? So it is very crucial that you have either positive or negative slope, so that I mean, you can move the current location to another supposedly better position, right? Okay, but remember the step function that we talked about. Okay, step function. Where is the step function? Yeah, this step function. I mean, if you draw the figure, okay, you will see obviously, okay, it is, no matter where you compute the value, okay, it's going to give you, the gradient is going to be 0, okay, the slope is going to be 0, okay, so that's the issue with this step function, activation functions, okay, so as a result, okay, they proposed, okay, to use a different activation function. Okay, there are three activation functions they propose to use. Okay, the first one is logistic. Okay, the second one is hypertangent. Okay, yeah, their definitions are given there. Okay, but I believe like you guys at least heard of these names, logistic, hypertangent, even though you probably don't use them very often. Okay, the third one probably is a new thing for you. Okay, but it is actually the easiest function. Okay, which is called rectified linear unit function. Okay, or abbreviated as a ReLU. Okay, ReLU. Okay, the ReLU basically like when the input is positive, you'll return positive value. When the input is negative, okay, well, it will just give you a 0. Okay, so these three functions obviously are nonlinear. Okay, because they are nonlinear, so they are able to, when they combine with remember each neuron has this step function, which has this activation function, right? So when all these neurons combined together, okay, they are able to deal with complicated scenarios, okay, and also, I mean, all these step functions these three step functions, they have like a gradient, okay. They may not have gradient all the places, but most of the places they have gradient, so that allows the gradient descent to work its way, okay, toward the optimal. Okay, so so here, okay, are the figures that show you these three, well, actually four different activation function. The the red line, okay, on the left-hand side, okay, the red line indicates the step function, which, as I said, okay, it works for the perception, but it's not good for the MLP because we are going to use gradient descent to train the model, okay? And the second one is logit. The logit is pretty much a logistic function, okay? So you can see the dotted line there is a logit one, okay? It's like this. From here to, so it is bounded. Its y value is bounded between 0 to 1, okay, from 0 to 1. Okay, and third one is the solid blue line, okay, it's a hypertangent, okay. It is also bounded, okay, its y range is also bounded by -1 to +1, okay, that's the hypertangent. The last one is ReLU. Okay, ReLU is a very interesting algorithm. Sorry, the interesting function. So when the input is lower than 0, okay, it will just output 0. Okay, so it's flat. Okay, when x value is lower than 0. Okay, but when x value is greater than 0, it is pretty much y equal to x, okay, it's pretty much a line, okay, straight line, okay, and their gradient, or you can say their derivatives, okay, first order derivatives, okay, are shown on the right hand side. As you can see, the step function is pretty much flat to be 0, so that's this why, okay, it is bad for gradient descent. You just have no gradient to work with, okay. But for the other three, logistic, hypertangent, ReLU, okay, at least we have some gradient to work with, okay. And the one thing you may feel strange is that ReLU, okay, when the input is less than is smaller than 0, okay, its gradient is also 0. Okay, but of course, when the input is greater than 1, okay, so greater than 0, the gradient is pretty much 1, right? The just a slope of the line y equal to x, right? So so you may wonder, in the ReLU must, it doesn't look like it's going to work very well, okay, in the multi-layer perceptron. But the result is actually very interesting, okay. Well, the logistic and the hypertangent, okay, and the ReLU, okay, for these three explanation functions, at the end, it turns out that ReLU has been adopted like much, the most, okay. It's because like ReLU normally performs much better than all the other activation functions, okay. This may be slightly against the intuition, okay. It is really because like most of the time you will see that, okay, the output is normally not necessarily smaller than 0, okay. I mean, remember like for a neuron, okay, it's going to get like an input from for a neuron in a hidden layer, okay, it is going to get like the input from all the neurons from the lower hidden layers, right? So what happens is that, okay, even though, okay, at some point of time, okay, its value may be negative, but most of the time, okay, its value is actually not that bad, okay. In other words, I mean, it received like it has like or let's put it this way, okay, it has like statistically speaking, like 50% of the chance for a neuron to have positive value, right? So for a neuron to have 50% of chance to get the gradient, it's already good enough for model training. Okay, well, we'll get to that, I mean, at a later point of the discussion. Okay, so these three activation functions, keep in mind, I mean, have been very important. Okay, after MLP training has been proposed. Okay, so the MLP, okay, can be used for different types of task. Okay, the first task, I mean, first type of task is regression. Okay, what is regression? Basically, the regression is that you use a model to predict a single value. Okay, for example, such as the price of a house. Okay, when you are given a certain number of features. Okay, or okay, you predict like the stock market, like you know, what's that? In Chinese we call it 指数, but I forgot the English term for that. Okay, I mean, for the stock market, normally you have a number to indicate like the current situation of the market, right? You can use the MLP to predict that number as well. Okay, of course, for a given number of features as well. Okay, so you can obviously also model that as a regression task. Okay, so in that case, your MLP will have a single output neuron. Okay, and its output is the predicted value. Okay, and you can also do what we call multivariate regression. Okay, what is multivariate regression? Okay, I believe you have seen some model that is able to predict like the to do like object detection, right? To do object detection. In the object detection model, it not only identify the type of the object, it also, you know, give you a window to bound to that window can, you know, it's a bounding box for the object. Okay, so in the picture, so this is like you know what the object detection model is. Okay, I will actually, we are going to talk about object detection model like at the end of like well, no, next chapter. Okay, so so think about this. Okay, when you want to output a bounding box for object, okay, you do need to have, for example, the center location of that object, as well as the width and the height of that bounding box, right? So for each bounding box, actually you need the center coordinate as well as like the width and height of that bounding box. So there are totally 4 numbers that are required, okay, for one bounding box. Okay, so you need to output you know, 4 numbers. Okay, 4 numbers here. Okay, I mean in the description of the slide, I mean, if you want to output like a coordinate, okay, just coordinate, I mean, in this case, it's like a center of the object, then just X and Y value, right? But if you want to have like the bounding box, then you need the size of the window. So there will be width and height. So for these 4 outputs, they are all numbers. And we call such a task as a multivariate regression. So depending on how many numbers you want to output, you will have to have like one neuron for each number. Okay. That's for the output layer, of course. Okay. So so when building a MLP for regression, okay, you do not want to use any activation function for the output neuron. Okay. So in that case, the output can be any value. Okay, positive, negative value, pretty much anything. Okay, but in certain application, okay, you want to, it is a regression task because, well, you want to output number, but the number you want to output, okay, may always be positive. Okay, for example, like remember like the object detection example that we talked about. Okay, no matter it's like the x and y coordinate as well as the width and height of the bounding box. Okay, all these four numbers are pretty much positive, right? And in the worst case, I mean, it can be 0, but that's pretty, I mean, they must be greater or equal to 0 anyway, right? So in that case, okay, you could use a ReLU activation function in the output layer, okay, for this to output these numbers, because ReLU, as you know, like its output is going to be greater or equal to 0. Okay, and another possibility, okay, other than ReLU, is the soft plus activation function. Okay, its its definition is given here. Okay, it's a log of 1 plus expz. So you can see that, okay, when z, okay, is negative, okay, the exponential of a negative value, okay, is going to be, very close to 0, right? So log of 1 is going to be close to 0, right? Close to 0. Remember, this expz is going to be, well, it's going to be 0 point something, right? It's still going to be positive. Okay, so it's going to be 1 point something. So log of 1 point something is going to be close to 0. Okay, when z is negative. Okay, when z is positive, or when z is 0, when z is 0, it's going to be log 2. Okay, log 2 will, depending on what your base is, okay, if it's like a natural number, then if it's e, okay, then, well, it's going to be smaller than 1, but somewhere between 0 and 1. Okay, and when the z is positive, okay, then the log 1 plus expz is going to be close to z. Okay, so this soft plus function, okay, is close to 0 when z is negative and close to z when z is positive. So in some sense, the shape will be similar to ReLU. Similar. I'm not saying the same, okay, but it's going to be, what should I say, smoother than ReLU. Okay, so and obviously because the output is guaranteed to be greater or equal to 0, so it can also be used as the activation function of the output neuron. Okay, in case if you are looking for the result to be greater or equal to 0. Okay, and if you want to guarantee the prediction, okay, will fall within a certain range, okay, then you may use either logistic or hyperbolic tangent, hypertangent, because logistic, we know the range is between 0 to 1, right? For hyperbolic tangent, okay, hypertangent, the range is between -1 to +1. So, I mean, in case if if that's not what you want, okay, that's not the range that you are looking for, you can scale it, okay, you can scale it to fit the range that you are looking for, okay. Even if scaling doesn't do the job well, okay, you can even do like shifting, okay, but basically like you could use like this like uh, hypertension or logistic, okay, for in the case if you're looking for like a you know, if you are looking for like a number that is within certain range, okay. So okay, for regression task, okay, the loss function can be, can be a mean square error, okay, as we have already seen in the previous discussion, okay. But if you have a lot of outliers, the mean square error, okay, may not work well, okay, because it will put too much emphasis on the outliers, okay. So in that case, you could use mean absolute value, mean absolute error, okay, to replace the mean square error, okay. Alternatively, you can also use Huber loss, okay. The Huber loss is kind of like a combination of mean square and the mean absolute error, okay. So um, the Huber loss is quadratic when the error is small and is linear when the error is large, okay. So it allows you to deal with the outlier much more effectively than the mean square error. But at the same time, because mean square error has the advantage of like a quick convergence, so the Huber loss, okay, also enjoy that quick convergence advantage, okay. So Huber loss is one, loss function you could consider, okay, in case if you have quite a lot of outliers in your training set, okay, in your training set. So here's typical regression MLP architecture I listed in this table, okay. This is just a reference for you, like in case you want to create an MLP for a regression task, okay. So this is like just like a reference. I'm not saying, you have to have the exactly same MLP architecture like what we have in this table, okay. But this table serves as a good starting point, okay, especially, okay, before you try anything else, okay. So as you can see, like one thing I want to point out, okay, for the activation function in the hidden layers, okay, you can see we prefer ReLU, or and you may ask, what is CLU? Okay, we are going to talk about CLU later. Okay, probably not now. Okay, so guess that's about it. So okay, so obviously, okay, the MLP can also I'm sorry, can also be used to deal with classification. Okay, for classification, there are actually different type of classifications. The first one is what we call binary classification. Okay, for example, like you want to classify, okay, either true or false for a certain event. Okay, um, um, if these true, true and false, they are, what should I say, like exclusive. Okay, for example, like the sex of a human. Okay, it could be male or female. Okay, well, I know like some people may say like there are some transsexual sex like option nowadays. Okay, but let's consider this problem more classical. Okay, classic. Okay, then we only have male and female. Okay, so things like the task like this. Okay, will be what we call binary classification problem. Okay, so so if it's a binary classification problem, we normally have a single output neuron, and we use logistic activation function. Okay, remember, logistic activation function will output a value between 0 to 1, right? So that value, that output value will be will represent the probability, okay, probability of a positive class. Okay, so for example, okay, remember I say like the sex, you may want to use certain attribute, or to predict a person is male or female, right? Okay, so so let's consider the positive class to be male and negative class to be female. Then if you get like a 0.7 output, that means this person is 70%, okay, likely to be male. Okay, and obviously it's going to be 1 minus 0.7, which is like a 30% chance to be a female. Okay, so this is the binary classification problem. Okay, and we also have like a multi-labeled binary classification task. What is multi-label binary classification task? Sometimes, I mean, there are some problem, okay, that has like a more than one binary classification. Okay, but this multiple binary classifications, I mean, they may not be, what should I say, like they may have certain correlation, but at least they are not disjoint, or they are not. For example, okay, let me give you an example that's probably easier. Okay, for you, for for example, sometimes we want to design an email spam filter, right? Spam email filter. Okay, so we want to classify if the incoming email is ham or spam. Okay, ham means it's harmless. It's a regular email. Spam means this email is it's harmful, or it's like it's maybe it's a phishing. Okay, he try to do some bad thing to your computer. Okay, and we sometimes also want, at the same time, want to predict, okay, if this email is an urgent email or non-urgent email. Okay, but so obviously to classify an email is ham or spam is a binary classification, and to predict an email is urgent or non-urgent is another binary classification, right? But for these two binary classifications, they are not necessary, because an urgent email, okay, can be, if you look at these two binary classifications, okay, a ham email, okay, can be either urgent or non-urgent. Okay, you may get a email from your friend, okay, I mean, just for chatting, Okay, so obviously it's not urgent, but you may get an email from your advisor, I mean, who wants you to report to him immediately. Okay, this is obviously an urgent email, right? So, but both emails are ham, right? But for spam, most likely the spam email, well, obviously it's going to be non-urgent, right? I mean, you don't have a spam email that's urgent. That sounds a little bit strange, right? Okay, but you can see that there are certain correlation between these two binary classification, but they are not exactly, what should I say, I mean, the output, you can sort of treat these two binary classification as two independent independent tasks. Okay, sort of, even though they are sort of correlated a little bit. Okay, so in that case, you just have like a two output neurons. One for each binary classification, and of course, I mean, just like the single binary classification, you still use like a logistic addition function here. Okay, and that should normally do the job well. Okay, so for classification, there's also another thing called multi-class classification, which probably is the most common classification task you will see. Okay, so in this case, each instance can belong to only a single class. Okay, out of several possible classes. Okay, for example, like one of the famous tasks is that you have some digital like a writing writing digit image. Okay, and we want to identify if this digit is it can only be 0 to 9, right? One of these 10 classes. Okay, so obviously that image, for a given image, it can only belong to one class, right? We call that as multi-class classification. Okay, so in that case, okay, we normally have one output neuron per class. Okay, and then we use softmax activation function for the whole output layer. Okay, so the softmax function will guarantee that all the estimated probability for each class. Okay, let's say like if it's like a written digit image. Okay, as I say, it could be from 0 to 9, right? 10 classes. So because as I say, like we will have one output neuron for each class. So we'll have like 10 output neuron, right? So each output neuron will output the probability for that image belong to that class. And the summation of all this probability will add up to be 1. Okay, so this is like a much natural, okay, situation that we are looking for. Okay, so this is called this type of test is called multi-class classification. So you may wonder like what is the softmax function? Okay, softmax function looks like this. Okay, for each class, let's say class K is going to be theta K to the power of T times X. Okay, and so that's for one class, right? The whole function, okay, is given below. Okay, so you can see that, okay, the because for the PK just means like a probability for the case class. Okay, so it looks like summation. Okay, at in the denominator, and the exp skx in the denominator. So you can see that obviously, okay, if you sum up the probability for all k, for all the k classes, the result will be 1. And also like this pk, the probability for the k class, okay, this value is guaranteed to be greater than, it's between 0 to 1, guaranteed to be between 0 to 1, because the no matter it's numerator or denominator, they are guaranteed to be greater than 1, greater than 0, right? Greater than 0. And the denominator obviously is a bigger value than denominator, okay? So this is like modern MLP with that is doing like a multi-class classification, and you can see we have like some hidden layers in between. We have like input layer, and in the output layer, okay, we will normally draw a softmax, okay, to demonstrate, to pretty much indicate like this is a multi-class classification problem. Okay. So this is like the typical classification MLP architecture. Again, okay, I just want to emphasize that this table is there just for your reference. Okay, it's not necessarily that your MLP model has to be exactly the same as what is listed here, but it serves as a good starting point, okay, when you design a MLP for a classification task, okay? And one thing we haven't talked about, okay, the loss function, okay, for classification, we normally use cross entropy. Okay, we will talk about this later, okay, when we talk about the programming, okay? So, well, it's already break, okay? Let's take 10 minutes break. When we come back, we'll continue our discussion, okay?